Alright, so today I'm going to be explaining another important paper with the title Susan, the Structural Similarity Random Walk Kernel. This STM paper in 2021 is very important. Random walk kernels, like previous video, they are very flexible family of graph kernels. So in the past 3 videos, I've talked about random walk kernels, and so in these videos I've been talking about them from different perspectives. Now this article is also relevant to that. There are very flexible family of graph kernels in which we can incorporate edge and vertex similarity through positive definite kernels. In this work, we study particular case within this family in which the vertex kernel has bounded support. We motivate this property as the configurable flexibility in terms of vertex alignment between the two graphs on which the walk is performed. We study several fast and intuitive ways to derive structurally aware labels and combine them with such a vertex kernel, which in turn is incorporated in the random walk kernel. We provide a fast algorithm to compute the resulting random walk kernel, and we give precise bounds on its computational complexity. So, given an alignment between the vertices of one graph, the alignment phi between the vertices of one graph to those of another, let me check something. So given an alignment phi between the vertices of one graph to those of another, one can count the number of simultaneous random walks between the two graphs. For example, here you see two small graphs G and H with the structural labels. 1, 2, 3 indicate as colors, and considering only vertex pair of identical labels. The product graph is C. Like in the previous videos, I showed the product graphs. And the product graph considered by the generic random walk kernel includes all pairs of vertices. So we consider the Kronecker product between this one. Is the Kronecker product between two matrices A prime and another matrix. We generally consider a pair of graphs in which case we implicitly refer to property of the first graph and the second graph. These are the property of the basic random walk kernels applied on two graphs is equal to the number of simultaneous walks between them. So this is how we write the random walk kernel. For example, counts all simultaneous random walks. And the choice of mu here, the choice gives rise to two special cases, geometric and exponential, like this. So this random walk defined here, this kernel defined here, has been extended or adapted in several ways. Like this one, it can also be generalized to in terms of these analytical expressions of equation 2,2. And alternatively, the same work used in conjugate gradient iterative solver to compute K of geometry And each iteration performs a matrix vector operation with a Kronecker matrix. We now introduce the graph coreness, a structural property that will be used in our kernel. A k-core component of a graph is an inclusion-wise maximal connected subgraph of G whose vertices U of all a degree of at least greater than k. The subgraph comprising of all k-core components we call it k-core. And then the reason underlying our use of structural graph properties is twofold. On one hand, the vertex labels on graphs might be unavailable or unsuitable as a basis for vertex alignment. Using structural properties as vertex labels allows the use of a multitude of available kernels on scalars for the evaluation of vertex similarity. So we can consider the structural vertex kernel, this case structural, as a kernel of attributes over the image of a feature map that extracts structure-aware properties. As its gradient goes over all pairs, it is rank 1, and the edge similarity matrix can be written as this W. So now we study the useful structure of Susan and analyze its computational complexity. We can plug in any integral structure attribute. The greatest efficiency comes with small bandwidth. So two natural such properties arise as particularly helpful. For example, vertex degree and its coreness, which can both be computed at virtually no cost. So they did experiments, and this is listing of p-values for the Welch t-test, comparing the performance of Susan using the coreness against all other kernels on the brain connectome dataset. If you like computational neuroscience, this is a very good dataset.